All right, so it is follow-up video time. I've got a variety of different problems. I am going to do all of the ones that involve the old exam last. So otherwise, I'm actually just going to go in order of material. So atomic radius is chapter 4. Those are exam questions. We're going to do those last. AMU in relationship to moles and the plum pudding model, those are all chapter 2. Electron configurations is chapter 4 as well. So we're actually going to go ahead and start with dealing with the plum pudding model and the gold foil. Why do they think alpha particles would go straight through? So to keep in mind where we are as far as thinking about what this is talking about. So this is back when we're trying to talk about Rutherford's gold foil experiment. And when we talk about Rutherford's gold foil experiment, gold foil, what they expected is they had a very thin sheet of gold foil. So this is my foil, and they're going to shoot alpha particles at this. And alpha particles are essentially a helium nucleus. So these are positively charged particles. And the expectation is that these will simply go straight through. So my detector's over here, and the assumption is that this is going to go straight through. The only thing that they knew about atoms at this point is that we had electrons, that they existed, and that those were in atoms, and they knew that matter was neutral. So they understood that since matter is neutral, there had to be positive stuff. So to think about why they are going to think that alpha particles are going to go straight through, alpha particles for them are just a type of radiation. We now know that this is a helium nucleus, but it's a type of radiation, and alpha particles go through things that are really super thin. They move at a really high speed. As far as a kind of radiation goes, they are relatively large. But essentially, they're thinking that if they get this foil thin enough, they're going to have such little stuff, and they're thinking that that the positive stuff is basically just kind of diffuse things, and that there are electrons hanging out in this diffuse positive stuff, like chocolate chips in a cookie. So this is actually where the plum pudding model comes from, because plum pudding is a British dessert that has plums in it and dough. It's the same general idea as a chocolate chip cookie. Chocolate chip cookies in 2 dimensions, plum puddings in 3 dimensions. So essentially, if you think about like the structure of dough, they really thought that the positive stuff was something that was not going to hold together very well. They really thought that this was something that was thin like tissue paper, and that your alpha particles were just going to rip right through it. That was the expectation. Now, keep in mind, they are also trying to come up with ideas about atoms. So, and they were wrong about this, right? This is not what actually happened. That's the entire point of the gold foil experiment, is that what does happen is that those alpha particles run into the nucleus, and the nucleus winds up deflecting those alpha particles. So if the alpha particle actually hits the nucleus, they wind up being deflected one way or the other. If they miss the nucleus, then they do in fact go straight through. So the other thing to keep in mind with the gold foil experiment is that your alpha particles, a lot of them did go straight through the gold foil. So most of them go straight through like expected. It's only a few of these that wind up either like coming back at the detector, or they wind up going off course. But the vast majority of them do what they thought it would, and the alpha particle goes right through the gold foil. So the vast majority of your data actually shows that you're correct, but they couldn't explain the ones that didn't work without the nucleus. So that's where the gold foil experiment shows off the nucleus. But yeah, so as far as why they thought that, essentially, they thought that positive stuff was not really substantial and wouldn't really matter. And they'd already messed with electrons enough to know that the mass of an electron was really, really small. So I just figured that the odds of the alpha particle running into an electron, that the electron's not going to do anything to an alpha particle, because an alpha particle was so much more massive than the electron, because they had the mass of the electron at that point. So that is what happens with that one. Okay, check mark. AMUs in relation to moles. So I had a chit chat with another student about AMUs and moles, and so I'm hoping that this is the same general idea. So keep in mind, when we have a definition for an AMU, that an AMU is 1/12 the mass of a carbon-12 atom. So please keep in mind that this is defined like this so that we have a unit in chemistry that is helpful to us to talk about the mass of atoms. So an AMU is an atomic mass unit. It's a really, really small number. I don't think I downloaded the potentially useful information. Oh, I did. It's right here. So thought an AMU was on here. There it is. So an AMU is 1.66054 times 10 to the negative 24th grams. So an AMU is really, really small. You can also see on here that it's not exactly the mass of a proton, and it's not exactly the mass of a neutron. It's a different number than those. So we really did make AMUs just to deal with atoms. Now, when you're hanging out on the periodic table and you're looking at things like this, so we're going to say that this is my carbon atom with average atomic mass on here. A lot of times we look at this number below, and the thing is that this number here actually has two different uses. This is the average atomic mass. So this is what we did a calculation on earlier, where you can say that if you had a whole bunch of different isotopes of carbon and you averaged them together, taking into account their relative abundance, this would be your average atomic mass in AMUs. So if you had one random carbon atom, granted, it would have an exact mass if you actually did only have one. But if you're trying to talk about what is it likely to be, 12.01 AMUs for one atom. This number, however, we're also going to use it as 12.01 grams in 1 mole. So if you had not just one random carbon atom, like we have over here on the left, but you actually had 6.022, there are more digits to this, by the way, but we only use a couple, times 10 to the 23 carbon atoms, supposed to be the word carbon, you should have 12.01 grams. So that's the other piece of this, that the AMU is an average atomic mass unit. So it's trying to talk about one atom, one on that scale, very, very small scale. The mole is trying to talk about things in real life, things that we can hold in our hand. So that's where we get this giant number. We do also, by the way, get this number still from carbon-12. So we still define the mole as being the number of atoms in 12 grams, number of carbon-12, I'm sorry, number of carbon-12 atoms in 12 grams. So this does sound kind of circular, but that's really because we want the AMU and this grams to mole ratio to both mean something and work together. So it does have two different units or two different meanings, one on an individual atomic scale, the other one on basically a human scale, where we can talk about how big things actually are in real life.